Hello everybody. So again, I'm Dr. Sergey Sarkisov, and today I want to show you an interesting problem and how to solve it that basically, I believe, drives the origination of calculus. So, calculus, right? Let me show you that problem that we're interested in maybe that is not easy to do in any other way. There are a few tricks, but nothing easy geometrically. So let's see. The idea I'm asking you to kind of incorporate is, let's say you have a parabola. Now everybody knows how to draw a parabola, right? At least y equals x squared. Right? And so if y equals x squared is graphed, let's say, between 0 and 1. Well, 0 squared is right at 0. So put x equals 0, and then the y value is 0. 0, 0 is a point. Let's go to, let's say, here's a 1. What's 1 squared? Well, 1 squared is a 1, right? Y is 1 when x is 1. So we just graph some coordinate points for the y equals x squared parabola. Well, let's see. What about 1/2? What if I square 1/2? I get 1/4, right? So it's right here somewhere. And that's going to be 1/4. Then if I square a 1/4, I get 1/16. So that's very, very small there. And so we're going like that, and that's our origination of the parabola, right? So let's do that. And then my question for you, question that I'd be interested in is, what is the area under the curve, under this parabola, between 0 and 1? In other words, what is my area right over here? What is that area? So, to do this problem, and again, we're going to begin with basic core roots of mathematics that we would have without knowing anything about derivative or integral, at least not yet, right? So let's do this. How do you find that area? Okay, so what are we going to do? Well, I don't really know. I can start guessing, start trying things. For example, I can try, what's a unit square area? What is area, right? It's basically a 1 by 1 square gives you that area of 1, right? 1 unit squared. So if I do the following, I say, well, here is my line, let's say y equals 1. That's how I would initially from 0 to 1 get a little picture of this square, right? Between 1 and 1, this is point 1, 1, and this is going to be the line y equals 1 right here. And then I'm going to stop here, and I'm going to say, look, the area of this is just 1, right? 1 by 1 box, square. Well, maybe the next thing I would want to try is, okay, well, this is 1. Let's try x, right? This is x squared, and I don't know what x squared is, but I can figure out, definitely can figure out what if I do a, let's see, y equals x line and find the area under the curve. I don't need calculus or anything for that. Look, y equals x, 0 goes to 0, 1 goes to 1. So there's a point like that. Very similar how this goes to 0, 0, this is 1, 1, 0, 0. I mean, sorry, 1, 1 here, right? So if I do y equals x, and I connect these 2 points, and that's the line y equals x, right? And underneath that, let's say, what's that area? Well, what's that area? It's going to be 1/2 of this base times the height, right? How you would do that for a right triangle, right? Or any triangle. Base times height, 1/2 of the area. Is that, so it's going to be 1/2. And so we have area here 1/2. Area here is 1, and then who knows what the area of that is, right? And I don't know any easy trick to figuring that out geometrically. So this is basically half of the box, right? We can see this is half of that. But what is this? I mean, what is it, like 1/3 of the box? And why would that be the case? Or is it, what, 1/4 or 1/5? And who knows what it is? Maybe it's some kind of difficult number. So let's see. What I'm going to do now, first of all, let's do this. Let's first look into what derivative is, okay? So a derivative, let me give you a definition of a derivative, okay? So the definition of a derivative, let's say we have no idea what it is, but here's the definition of derivative, okay? We kind of know the limits, hopefully. So if I do f prime of x, okay, let's write it that way. So derivative of f, the function at x, whatever that is, it's going to equal to, by definition, again, let's say we don't even know what this means, we're just going to write limit, x goes to, or let's actually say h goes to 0, okay, whatever that h is, okay, it's going to be the little distance between the jump between the change in the x that I'm going to do. So I'm going to say, okay, f of x plus h. So I'm adding whatever that f of x is, I'm going to add a little h to it, plus, minus so the difference between that and just f of x, all over, let's just, instead of saying h, I'm going to say x plus h minus x, right? And so I'm going to write this, and I'm going to erase it as what's x plus h minus x. The x's cancel, and you have just an h. Okay? Now, I just really gave you the definition without any meaning behind it. Okay? To show you some meaning behind this, what's the conceptual understanding, graphical, maybe what that could be, is let's do this. Let's try to graph some kind of function, maybe even like a parabola, but anything going on. Let's say I have like that. Okay, some kind of function, and of course it can go, anywhere and from anywhere to anywhere, any function, f of x, right? And so let's say I try, well, here is some point, let's say x. Okay? That's some x value where I'm at, and then this is going to be the height. What's the height? Is f of x, right? Or whatnot, right? Let's try, this is a function, I'm going to get rid of f of x here. And so what if I do x plus h, a little h in addition to the x, so move it a little bit to the right of the x. Well, that's going to be what? What's that going to be? That's going to be a height now. The function value of that at x value, at this horizontal value, x plus h, is now f of x plus h, okay? And so what I'm actually doing, if you look at just this part, right, that part, without the limit part of it, this slope between this point and that point, okay, the slope, what is that slope? The slope m, okay, let's call it m, is the delta y, right, the delta y over the delta x. And that will be exactly f of x plus h minus f of x. Write that here, f of x plus h minus f of x, okay, all over what? This minus that, right, the change in the x's, and that's going to be x plus h minus x plus h. Okay? And that looks very much like that, doesn't it? This expression there, right? And now if I'm taking limit as h goes to 0, what happens is, instead of it being here or there, the slope of the line between these 2 points becomes the slope of the line basically at this point. And it's going to be, as you can see, tangent. It's a tangent, slope of the tangent line at this point to the function, okay? And that's a quick glimpse of this, what derivative means graphically. Of course, it takes a little more insight or a little more time to really grasp this by doing this over and over. But the idea being, let me erase it just a little bit more and show you one more time. So let's say I gave you a point, and of course h now looks a little bigger than just 0, right? When I take limit h goes to 0. So what I do is I'm like, all right, well, let's say I'm adding some kind of h that's not 0, not going to 0. So here's a point. Okay, there's my slope. Oh, between of this line, right? And then let's say I have this, and then I get a little closer. I get h smaller, right? Then it's the slope of this line, and then the slope of this line. Oh, the slope of that, basically that's a tangent, right, to the curve again. The slope of the tangent here, slope, right, this is a slope, basically the tangent line at that point. So that's hopefully a graphical understanding. Can give you a graphical understanding of this, what the function and the slope of that function at that point would be. It would be actually the derivative, based on just this definition and how we grasp it. So I'm going to do a little better picture here. Again, let's say that this, and here is my, well, let's do this. It's a little messy here. So let's do this, and then here we are with, here's a point, and we have a point there. That's going to be that slope, and then we have a point here, that slope, and finally we get this, whatever that is, slope right there for the tangent line. Okay. So this here, when h goes to 0, okay, makes its slope of basically the line became not just this random line, but like not the secant line, but just specifically that line tangent at this point of the function. Okay, so slope of m of tangent. That's what this h goes to 0 does. Tangent line. the graph of the function. Now, so that's derivative, kind of the graphical understanding of it based on the definition, okay? The other thing I'm going to do for us is this. Okay? I'm going to talk about a little bit of something kind of reverse of that. Let's say I'm interested in area. Right? So I give you, let's see, I give you some kind of similar function to that, or just any function, maybe some polynomial or something. And I'm going to do this. I'm going to say, well, let's say I have, it goes from, let's go from 0 to something. So maybe I'll go like that, and it goes on and on, right? Some kind of function. And I'm interested in what's the area. Now this is different, right? I'm not talking about the slope and the tangent line of any, or the change, rate of change or anything, right? Because how fast something changes, the slope is actually rate of change also, how fast something's changing. Think about this being the time axis. And let's say this is how much money you have. Well, per time, how much money you're going to have, right, is changing. So you have a little bit here, and you have more here, you have less here, you're at 0, you're zero balance, you're negative, you're in debt, basically. That's sometimes I'll give those examples when we talk about functions and money versus time. Makes a lot of sense, right? Anyway, let's talk about areas. So I'm going to call area I, the function. In other words, let's go from 0, right, that's a 0, let's go to x. And I'm going to say, look, the area, it's like a running area, right? So I'm just going to say, this is I of x, the area between 0 and x. And if I do, let me just write it so like that so you can see that's the area. Okay. And then what if I do a little bigger, again, h, add an h and say x plus h. Now h is going to be, again, we're going to limit this h going to 0 eventually, but let's say I go here, and what happens? Well, this area here, all the way to this, right, is going to be I, this area here is going to be basically all of this. It's going to be I of x plus h. Okay? So the area of this is I of x. The area of this bigger piece, right, in addition, let's see, I'm going to add, I'm adding, let's do this a little bit in different color, just to be understand more. So this additional piece in blue, right, with the original green piece, that's going to be the I of x plus h. So that's area. Now, well, what does that do for us? Let me try something else. Let me try to just construct a little argument with how, what's the height, basically, what's this function value? What is, this is again, you know, the green height, whatnot, this is the function f of x, right? So let's try this. What is this f of x here? What's this height? Well, let's do this. Let's try to just write something that we maybe have no idea why we're doing this initially. But let's say, what's the limit of, as h goes to 0, of I of x plus h minus an I of x all over h. The reason I'm doing this is because, well, at least for now, if I had nothing else to do, I was like, well, I see something similar. I have a function, some I of x plus h, which is area between 0 and whatever that I of x would be in any x, right? Of this, under any curve that I'm given. And I'm like, oh, why not? Like, let me just try this, whatever that's going to be. What is this? What's this physical? What's this kind of graphical meaning of this? Well, actually, if you think about it, forget the limit for a moment. And then, again, I'm trying to relate it a little bit to the derivative. Again, this is actually, what this is derivative, right? So first of all, by definition, you can copy that a little bit. I'm like, all right, this is f here. That's going to be, so it's I, right? Match it up. So derivative of this area, whatever that means, remember this is area. From 0 to, right? This is area. From 0 to x here, I of x, and this is from 0 to x plus h. Okay. Anyway, so I prime of x, it's really just mimicking, but the derivative, the definition of derivative is that f prime of x is going to be that. Well, then I prime of x is going to be this. Okay. Let's see something else. What is I of x plus h minus I of x? That's the blue area, isn't it? That's that's this area minus that green one, and that's going to be the blue area. So that's going to be equivalent to, let's say equivalent to blue area, right? Little box area, a box of that little chunk there, okay, all over, let's go back to this marker here, all over what? All over h, the base. That's like kind of a base there, right? H right there. So that's going to be a little all over h, let's say, for now. And what's this area of the box? The area of the box, and this is a very small box, again, h is going to 0. And the reason we're going to do h go to 0, h is going to 0, I'll show you in a bit. But, yeah, and you know what we're doing actually? It's called the Fundamental Theorem of Calculus. Right away, we're doing something interesting here. We're doing the Fundamental Theorem of Calculus. You rarely hear it right in the beginning of a calculus class. And so I want to show you, again, I'm trying to actually solve a problem. What's the area under a curve, parabola, from 0 to 1? Now, it's nothing to do seemingly with any of this result and any of this making up of derivative, what it is, and what is this area stuff, right? But, again, remember, we're trying to find area right there. So that's why I'm kind of pushing for it. Let's try some area stuff here. And again, for some reason, we'll need this derivative. Let's see. So blue area of this little, right, this little, what's left here, this rectangle. And again, it's little because h is going to 0. It's going to be small. X with x and x plus h is basically x and almost on x as well. So the blue area of this box, now this is going to be what? The height of that, well, f of x, right? Whether it's f of x plus h, which is, you know, h is going to 0, so it's basically, you're just right here. And the height is f of x, right? From here to there, that's the y value, that's the height. So this is going to be f of x. F of x here. Let's see, get another marker here. So f of x. And what is this height? Well, what is this base? That's h, right? So what's the area of a little box, a little rectangle, kind of vertical rectangle like that? Well, it's equal to h, right, the base times the height. And then we're dividing by h, aren't we? Right there. Cancel, cancel. The derivative of area, ongoing area, from left to right. Derivative of ongoing area from left to right. It's what? It's the function. It's the function value. That's the fundamental theorem of calculus. Well, at least much of it is, that basically this thing, the area is covered, it's really the integral. That's why I'm using I. We don't really know necessarily that right now. And maybe you don't want to tell anyone, hey, you know, professor taught us this one of the first days of class. You're not supposed to do that really, right? But just remember this for later. That derivative of the I, the area, the moving area, kind of with the integral, the going back on the derivative will be, so the derivative of the area stuff is going to be the function value, just the original function value. Now, let's try this. Let's see what we can do here. So, I want to know area. I don't want to know change in area or derivative area or anything like that, but I want to know the area from 0 to 1 of under the parabola. Now, I know the function. My function is x squared, right? So, what can I do here? Let's see. Let me show you something interesting. First, right? Let me show you how would you find a derivative of something, some function, such as, let's try this, x cubed. Another function, why not, right? So what we can do is, we're going to erase this out for a moment, right? Okay. Erase this part. Let's just erase it all. We're going to get back to this. So, this is a little better. So, now, what we're going to do is, we're going to just try this derivative of what? Let's try the derivative of a function f of x is equal to x cubed. Maybe we don't know why we're doing that right now. It doesn't really matter necessarily. But, at the moment, but what? Let's just find the derivative of this, and that would be by using the definition. So we're going to be, all right, f prime of x will equal to what? What's f of x plus h? And the limit, right? So limit as h goes to 0. The f of x plus h, I'm using this definition. It's going to be, well, I'll put an x plus h in the, I'm cubing it now instead of x, right? And then subtract the f of x, well, we know it's x cubed, copy that, right? All over h, okay? And then we kind of expand a little bit, do binomial theorem. We're used to this a little bit now, right? More so than not. So we're going to say that this is equal to, now if you know what this is, or you can take your time doing the expansion of this, right? X plus h times x plus h squared, or binomial x plus h cubed. We get x cubed plus 3x squared h plus a 3x h squared, and plus that h cubed. And take away, of course, that x cubed at the end, okay? All over h. Okay. Now look, what we can see is the h here will cancel. This h, the square will go away, right? H squared over h, that's going to be just h left. And h cubed over h, this is going to be a square here, right? And then everything else, notice this x would have gone away with, and I'm trying to kind of do this in a quicker manner, right? So that's why I'm showing you all these kind of steps in one. The x cubed minus x cubed, actually that had gone away. And what we have is the limit as h goes to 0. What's the only step remaining? That's why and by the way, we didn't have to divide out the h from x cubed because x cubed and minus x cubed initially canceled. Okay? So what we're going to do is we're going to be, all right, we're left with 3x squared, and remember the h is canceled, plus a 3x and the h here, 1 remaining, and then plus an h squared, right? That was the one thing that remained there from the h cubed divided by h. And then, of course, h going to 0, the only thing remaining is 3x squared. Okay, well, why do we do all that? I have x squared. I wanted to find the area under x squared. I know that the derivative of x cubed is x squared. So watch this. The derivative, x cubed, and then I do prime, the derivative, and it gives me 3x squared. Okay? Interesting. Because what actually is going on? What's going on? Let's go back to this, all these ideas we had. The area, okay, if you're changing, you're getting that change in area, if you're getting that derivative of the area, what's happening? You're going to get that function back. Now, what if I want the area? So if I differentiate the area, I get the function. Okay? So if I differentiate the area, I get the function, for example. In other words, let's say I of x is equal to x cubed. Then I prime of x, just like we did there, is going to be 3x squared, right? And that's going to be my function. And remember, I care about what? I care about the area. So we have a function for finding the area if I give you a function 3x squared. Going back on it, I know that the area under the 3x squared will be x cubed. Let me say that one more time. This is very important. So whatever I have here, that's the derivative of the area if so. And we know the derivative of this is derivative of actually x cubed. I just have done that for us, right? So if the x cubed were the area, then the I prime, the area prime, the moving area, would be 3x squared, because the derivative of x cubed is 3x squared. And we know that I prime, the moving area derivative of it, we've done it here, is going to give you back the function value, or the function, right? So the function, if it's 3x squared, the area under it is x cubed. Now, what I'm going to do now, very important, is let me divide this by 3, and this everything by 3. Okay, and I could have just done, for example, I could have done, instead of x cubed, I could have done x cubed over 3 initially. I didn't really want to confuse this at that point. But if I just divide everything by 3, we basically have that the 3's would cancel. Okay. And if so, our x squared, if that was a function, x cubed over 3, would be where it came, would be the area of that function. So what this gives us is the result. So I'm going to write that here. Therefore, the area I of x under f of x. Okay. Let me first do that without these x cubes and x squared specifically. So therefore, the area I of x under f of x is equal to, what is it? It's antiderivative, right, of f of x. So if f of x is the derivative of the area, how do you get the area? Go back on the derivative. It's equal to antiderivative of f of x. Okay? Let's erase all this. It's actually the fundamental theorem of calculus. And let's see how we can apply it to specifically our problem. Because again, we're almost there. If you think about it, be thinking on your own. How would you solidify that from 0 to 1? You're finding the area under that parabola. Okay? So watch this. Here it goes. It's kind of exciting. I'm excited. Watch this. Let's say my function is, again, remember our function is f of x is equal to x squared. That's a parabola. We draw that and we find the area here. It's 0.011, right? It's 0.00. It's origin. And this is my function, f of x is equal to x squared. Now, we know that this x squared, what's the antiderivative? Well, remember, x cubed went to 3x squared. By this, we did it here. X cubed goes to 3x squared. Divide everything by 3, that's a linear argument. You can do that, and again, if I told you x cubed over 3, everything would be divided by 3, you would have gotten just that. 3 over 3, like I said, x squared. So if I do 1/3 x cubed, it will give me a x squared. Now, if I want this to be the function, this will be my area. Remember going, because I prime, this is also I prime, is f of x. So this is my I of x, area. Okay? So it's 1/3 x cubed. What's the x right here? Because I said from 0 to 1. So where am I actually ending? I'm ending at a 1. And so my area under y equals, or let's say y equals x squared from 0 to x equals 1. About to get this result. Watch this. Is equal to I, the area, I of x equals 1, which is 1/3 x cubed when x equals 1. So 1/3, 1 cubed, and that's exactly 1 over 3. Guess what? I kind of said that initially, maybe it's 1/3. Remember, we had the square, area is 1. Y equals x line, area is 1/2. And guess what? Y equals x squared is 1/3. Y equals x cubed under the cubic. You guessed it, it's 1/4. You can do the same thing. Right. Thank you so much. I hope you enjoyed this one. It's a very beautiful result. I think it's a beautiful problem, finding the area under y equals x squared, that drives this calculus, initiation of calculus and the demand for it. Okay? Anyway, have a great day.